Nanjing, the capital of Jiangsu province, is an ancient capital of the Six Dynasties with profound historical and cultural heritage, and a modern international metropolis that is friendly, livable, tolerant, and open. Nanjing University of Science and Technology, established in 1953, is located in the most beautiful Zhongshan Scenic Area of Nanjing. It is a national key university affiliated to the Ministry of Industry and Information Technology. Upholding the motto, dedication to truth and innovation, NJUST actively integrates into the country's manufacturing and network construction, the Yangtze River Delta region development, and other major national strategies and regional economic and social development. With the strategy of one university and 3 campuses, NJUST has been committed to multidisciplinary development on engineering, science, medicine, human sciences, management, economics, and law. As a key university of 211 Project, a member of 985 Innovation Platform, and a double first-class construction universities and disciplines, NJUST has been dedicated to mounting up to the plateau and peak of superior diversified disciplines. The university has 4 disciplines ranking in the top 1% of ESI disciplines, with engineering is in the top 1,000th globally. The university has 15 academic colleges, more than 2,000 full-time faculty members, 20 academicians, around 30,000 students, including 1,000 international students. Innovation is the key to the university's academic excellence. NJUST has more than 50 research platforms at the provincial and ministerial levels or above, and has undertaken a large number of major national scientific research tasks. NJUST has made fruitful innovation achievements on the way of continuous improvement in basic research capabilities and deepened coordination of industry, academia, and research. It has become an important base for scientific and technological innovation in China. NJUST has won 105 national scientific and technological awards, including 9 national first-class awards. As an academician of CAE, Professor Wang Zishan won the 2017 National Super Rim Award for Science and Technology. NJUST has been optimizing talent cultivation mode. The university devotes itself to cultivating innovative and elite talents with international competitiveness to lead the future. More than 230,000 NJUST alumni have graduated and been serving as innovative academic leaders, industrial elites, and pillars of governance for the country. NJUST students have won many awards in major events such as the Internet Plus Student Innovation and Entrepreneurship Competition, the Challenge Cup National Extracurricular Academic Science and Technology Competition, the Postgraduate Innovation and Practice Competition, ICANN International Contest of Innovation and International Collegiate Programming Contest. NJUST vigorously promotes the process of internationalization and has established close cooperation with more than 200 famous universities and research institutions abroad. With joint efforts, NJUST has established international cooperative bases such as Herbert Glader Institute of Nanoscience with KIT, Sino-French Engineer Institute with the University of Lorraine, Technology Innovation Support Center with the World Intellectual Property Organization, to carry out cultural exchanges and promote mutual understanding among civilizations. The university has set up research centers on the Kingdom of Saudi Arabia, the Republic of Belarus, Central and Eastern Europe. Stepping into NJUST campus, there is strong academic atmosphere, where elites and masters work side by side. Here stand the verdant and upright forest, the elegant Zixia Lake. Students embrace the vibrant campus life. Here, the pulse of Chinese history and culture can be touched. Students experience the speed of development of modern China. On the pursuit of truth and innovation, steps never stop. Explore the world of new knowledge and meet the bright future at NJUST.
In today's challenging environment, scientists and engineers need to accelerate discovery processes. CAMICA offers unique, high-performance analytical instruments to help them unveil the secrets of life and materials at the micro, nano, and even the atomic scale. Founded near Paris in 1929, CAMICA rapidly established its name by pioneering first electron probe microanalysis, followed by secondary ion mass spectrometry, and more recently, atom probe tomography. Ever since, we've maintained our R&D investments at their highest level and partnered with leading academic institutions in order to explore new techniques and technologies. Today, CAMICA is part of the Materials Analysis Division of AMETEK, a global manufacturer of electronic instruments and electromechanical products. We have locations all around the world and strive to expand our reach to new geographical frontiers in order to foster emerging scientific players. Our state-of-the-art production facilities in France and the US allow our experts to develop the most sophisticated microanalytical tools used for research and process control applications in materials, semiconductors, geology, environmental and life sciences. Huge investments are made worldwide towards the development of stronger, lighter and more durable materials for transportation, energy production, aerospace and defense, and consumer products. Materials scientists rely on CAMICA instruments not only to gain a deeper understanding of the properties of materials, but also to predict their performance in real world. CAMICA also accompanies semiconductor manufacturers as they explore the boundaries of physics. Our metrology tools enable the production of latest generation electronic devices, contributing to a world where communication is faster and more reliable. From understanding the microstructures of rocks and the genesis of the solar system to revealing water and soil pollution processes, CAMICA provides the tools for writing the history of the universe and creating a safer environment. Offering novel and powerful instruments for studying intra- and transcellular metabolic pathways, DNA expression, virus penetration, and drug localization, CAMICA enables important medical advancements. Thanks to such a wide spectrum of applications, our instruments have been adopted by top-ranking academic and research institutions, as well as major industrial corporations all over the world. Their satisfaction and success are our main focus. The expertise and passion of our teams will enable us to further push the limits of microanalytical instrumentation and help our customers reach the highest performance in their specialized fields. CAMICA, Science and Metrology Solutions.
Close your eyes. What do you see? Do you see yourself, the path in front of you, the next step? Do you see your ambition, the cutting-edge approach that opens new dimensions in medicine, the biggest miniaturization that lays the foundation for the digital revolution, the holistic perspective that transforms humanity for good, the progressive vision that changes everything, the way you see the world, the way you capture moments, the way you transcend knowledge, the way you define precision and productivity, the way you live, move, love, heal, think, are. Open your eyes. Can you see it? Together, we are challenging the limits of imagination. For those who see beyond. Zeiss. Seeing beyond.
Good morning, everyone, or I guess good morning, good afternoon, and good evening. I think everybody should be able to hear me. Hi, my name is Daniel Perea. I'm a senior research scientist at Pacific Northwest National Laboratory, and this morning I have the honor of chairing this morning's first session on this last day, and the session is the 11th technical session, Geological and Biological Materials and Functional Materials. And we have um, five speakers this morning, and starting out with Professor Jing Fu, who has an invited talk, and then we'll have 4 contributed talks. However, unfortunately, the second to last talk by John Popolowski, he was unable to make it after all. Something I'm not exactly sure what happened, but he won't be able to be giving this talk. So we're going to intentionally leave that space blank, and then we'll take a short break and then come back for the last talk of the session, just so that we can.
Danny,
go ahead.
So I will use John's time slot to give a short presentation to thank everyone. Okay.
Oh, excellent.
Yes.
Okay. Thank you, Gong. Gong just stepped. Excellent. Okay, so we'll keep that time slot available, but it won't be John's talk. So Gong will help fill in that space, and then we'll keep the time accordingly. Okay, I will speak up within about 3 minutes of everybody's talk to give everybody a heads up about the talk, your time coming up to an end, and then to leave some time for some questions. With that, I would like to introduce our first speaker of the morning. Again, Professor Jing Fu. Dr. Jing Fu is currently a group leader and a senior lecturer in the Department of Mechanical and Aerospace Engineering at Monash University in Australia. He obtained his Bachelor's of Engineering from Shanghai Jiao Tong University and a master's from Hong Kong University of Science and Technology in 2007. In 2008, he received a PhD from Penn State University with a focus on manufacturing engineering and microfabrication. In 2008, he was awarded a postdoctoral fellowship from the U.S. Institutes of Health, so NIH, National Institute of Health, to continue his research and specialized biology training at NIH with the Maryland campus. During the course of his fellowship, Dr. Fu explored a number of world-first projects, including the integration of cryogenic focused ion beam with cryo-EM and 3D fib-SEM tomography of virus cell interfaces. He was also involved in exploring bioimaging with Atom Probe via collaboration with the company Imago at the time, and acquired extensive knowledge and experience preparing different types of biological model systems. Dr. Fu is an international frontrunner of employing FIB and APT to investigate atomic and molecular signatures in biological cells. Training in both engineering and biology has enabled him to make significant contributions to the advances of FIB and APT for frozen hydrated specimens, which are really desirable in life sciences. His group first reported applying thin conductive coatings to disguise the surface of insulated and biological samples, followed by imaging with APT in voltage mode, which is considered to work only for conductive materials. The successful imaging of bacterial cells with APT provided the atom by atom view of antibiotic resistant bacteria, or also known as superbugs, revealing compositional changes potentially linked to resistant mechanisms. Dr. Fu's group also explored graphene encapsulation, a new route for liquid imaging without the need for cryotransfer systems, and recently achieved direct APT imaging of proteins and nanoparticles in solution. Dr. Fu's research interests also include tuning nanomaterials by charged particle beams to fabricate unprecedented 1D and 3D nanostructures. The fundamental insights of how dynamics are produced at nanoscale provides knowledge to precisely control the nanostructures for preparing novel site-specific samples for APT imaging. So with that, I'll hand it over to Dr. Jing Fu and hear from him. Thank you.
Yeah, thanks, Danny. Can you hear me? Good. Yeah, thanks, Danny, and also thank you, Professor Gang Xia. I gave a similar talk 4 years ago. I was invited to Nanjing. It was a really memorable experience. So I just want to give some introduce or give some some of the recent progress we have. And so I used the topic about the export dynamics at nanoscale. So imaging the biological samples, it's actually require a quite like a paradigm shift compared to inorganic materials. I was trying to put the co-authors, but unfortunately, the list is too long. So I just put a acknowledgement of this. It's involved many many people from different disciplines, and I'm quite proud that we can actually doing things together. So just a brief introduction. It's interesting that the cell was considered a biological atom back to the 19th centuries. And because the microscopic advances, so we actually can look at more details. So now we know that's actually a delicate machine, a molecular machine. So decide how we are born, how we are becoming sick. So there will be quite a recent success of APT imaging for the biominerals. So we can see lots of fantastic results. So our study is more focusing on the cellular part. So that means we actually look at the hydrated samples, which is more challenging, but it's also quite exciting. So cryo-fiber is so most of you probably heard of cryo-EM, which is starting from 1970s or 1980s. Was a very well established and changed lots of fundamental research topics. So my main interest was primarily like a cryo-fiber tomography, which actually can look at the cells, whole cells in 3D. Then back to 2010, so I accidentally entered APT&M probe because my postdoc supervisor had a chat with Tom Kelly. Back then was Imago. So they decided to have a go with cellular imaging with APT. And I was told it was a quite straightforward project, but it turns out that there's many years research has been spent on that. All right. So this is just a review. What would be the best way to actually look at the cellular samples, right? So the cryo or atom probe tomography is really at the bottom, right? But it's given an impressive resolution and also provide a chemistry, which is very, very desirable. So is that possible to become the next cryo-EM? So that's the question we have, right? And we really look at like in 10 years time, or maybe 20 years time. So the first study is we actually with Imago is we can actually dehydrate the mammalian cells, and then we can do a lift out, and then we can actually successfully probe the cellular samples, which is dehydrated. We also attempt the cryo, but it was quite challenging at that time. So my group also looked at the bacterial cells. We actually have found it to look at antibiotics resistance. So we took the bacterial cells, also dehydrated. So we actually look at the cryo-EM in the parallel, which only give the structure information. And also it's fairly hard to identify because they basically look at the same in the membrane area. But with the APT&M probe, we actually can look at the chemistry at the cell membrane. And we do find some quite a difference, and particularly in the cell membrane structure, which was expected. But that's actually the help the bacteria to fight the antibiotics. So I still want to present this. I presented this maybe 4 years ago in Nanjing because in the back, basically that is the best example for the people in Nanjing, I think. So depending on your skill and depending on sample preparation, so we actually for chemical mappings, so we actually can have to keep it like a freeze drying or frozen, hydrated, okay, to keep it chemistry. And the preferred that we can have a live, right, and or hydrated or untainted. But there'll be actually quite some discussions about whether it's worth to do live, right, particularly in the high vacuum system, because the information you get is more or less the same as the frozen hydrated samples. So it's really, we actually don't have lots of actually a choice, right? So preferably we can have either frozen hydrated, right? And if you can have a vitreous ice or freeze drying to keep the chemistry, if we are aiming for chemical mapping, just like APT&M probe. So we actually, the big two questions or the big two aims is, can we actually stop to produce a sub 100 nanometer vitreous ice samples? So this is the foundation of cryo-EM is based on the discovery by Duvershut. So if you have a thin film of liquid, you can actually rapidly freezing to actually forming the vitreous ice, which is avoid the damage from the crystalline structures, right, causing to the biological samples. So can we do the same as a vitreous ice needle, okay, for the cryo-atom probe, and also to establish a high throughput, a damage-free transfer. So we don't want to damage because once you have once you have cryo samples, if you are above 130K roughly, so you actually have introduced the crystalline structure again, which would damage your sample or destroy your samples. So this is the two big questions or big aims we have. So we actually starting with different type of coatings, starting from the metal coatings, and then in 2017 or 2018, so we actually started explored using a graphene methods as a conductive coating. So by just etching the graphene in the liquid, so you can slowly move that the wiring and slowly onto the tip, could be a tungsten tip. Then the result you will able to is we do see the wrinkles, right? And it's not very visible in the SEM, but if it's the high resolution DM, we can actually look at. So it's a very nice coating layer, which is conductive. It's also very strong. So we use this method just to coat different type of the insulated material and biological material. So what we found is even into a voltage mode, we can actually successfully image those material or samples. So this will give us some confidence to go to move on. So also we actually by changing the speed of a coating, right? And when we reduce to a several micron per second, so which are very slow, controlled by a digital manipulator, so we can actually trap a certain liquid. Right? So there was discovered quite accidentally. So this is the innovation of how this is being done, right? So there are certain liquid will be actually trapped in the tip of the tungsten tip, and if we can control the geometry, it actually will be suitable for atom probe probing. So there's a certain initial test. So we coat the different layers, coated twice. So that means that there are two water layers. So this is by super resolution microscopy with a fluorescent dye. So this is obviously there's actually liquid already trapped, and also is accumulated with more layers. We also look at with the FIV-SEM, so we cut the cross section. So the cross section with so in the middle, the core is actually the tungsten tip, and surrounding this is a frozen liquid. Right? The outer layer of the graphene is not visible here, but we know actually be there because that's way before doing the freezing. All right. So we did a few probing. So we actually started to think about why we instead of doing so the first time I heard of cryo-atom probe, so I was a little bit confused because the sample stage are already cooled. So almost every time you're doing the cryo APT already. So we think about rather than transfer the ice to the place where it's already very cold, right? Why not just transfer the liquid? Okay, if you have a method which can actually sustain in the ambient and also high vacuums, so you can transfer the liquid, a small volume liquid, immediate to the sample stage to freeze. So we prepared the squid and we put them into the atom probe. So that's one of the early days. We actually look at one of the earliest samples. We look at the water volume, and in the state it's already in the ice state. It's freezing on the APT sample stage. So we can obviously see the species from the water layer. So the volume was actually fairly limited in the beginning. So later on we actually try to tune so we can get in a large volume compared to the initial test. So this gives us some quite interesting results because we don't actually need a cryo transfer system. So we can directly put the liquid, right, and move to the atom probe for probing. So this gives us some of the application is, for example, we can actually look at the protein, which is actually in the liquid. So the protein sample will be actually trapped, right? So directly input the atom probe for probing. So that's the sum of the results. So we can, because the ferritin, we can clearly see the iron signals and the different species from the core and shell structure. So that's the example of. So it's also there's parallel, we have the cryo-TM looking at. So this is actually TM. So we also have the cryo-TM we can look at because it's the graphene already encapsulated. So it's quite easy for transfer because you can transfer in the ambient or you can put in your pocket even. Or you can also put in all kinds of different high vacuum system for imaging. So that's the mass spectrum, and this is the final reconstruction. So there's still lots of work to do because we only capture a certain a portion of we believe we only capture a portion of the protein particle. It's just still a stochastic process because we cannot precisely which location. But most cases we can actually capture a part of the protein side. And also by 3D reconstruction, we can actually look at clearly have a co-shell structure which are living. So that's also basically contributed by the preparation because the graphene and also the freezing, on-stage freezing actually maintain the structure of the original protein. That's another example is we also I've shown before, so I just quickly go over this. So there's also another particle in liquid in the solution. So this is so the graphene encapsulation we can actually keep. There's also liquid, the solution inside. So you can see the nanoparticle is just sitting like basically floating in the liquid. So the geometry is we can control it in the less than 100 nanometers. So which is actually we can transfer to the atom probe for probing. So this is the mass spectrum we obtained from the graphene coated layer. So for most of the samples, we don't see a strong carbon signal. It's probably the mass of the graphene is so quite limited. But what we do find is once we have the reconstruction, so there's a concentrated gold area. So that's the gold nanoparticle. It's also a part of the gold nanoparticle because the field of view is quite limited. And also there's a certain randomness involved where the location of the nanoparticle. But we do find clearly there's a liquid from the water, and also there's in about the 2 nanometer layer at the interface from the nanoparticle to the water. There's actually accumulation of the chemical species. So which is actually from the solution we will prepare the nanoparticles to prevent the aggregation. Okay? So this is basically what we can see is how we can actually tune the assembly of the nanoparticles, because you're probably always getting a small, like a several nanometer layer interface between those nanoparticles. So which was very obvious until you're actually using an atom probe to look at it. So again, we didn't end up using any cryo transfer. We're just using the graphene method, which is kind of gave us a quite clean signals from the sample. So more recently, we are interested is, so the big question is, how do we actually prepare the visual eye sample? So just like the cryo-EM. So personally, I think that's quite important, which will actually decide whether the atom probe can be moved to the next stage is for the actual biological particles or like proteins or DNA. So we actually tried a number of methods to produce the visual samples. So there are a few are successful, and there are also some of the failed. So one of the successful is called open microcapillary. So we machine just to get feedback, create a small slot. So the slot you can actually, by tuning the slot and the different type of liquids, we can actually trap a small volume of the liquid initially into the slot. Then we can put into the liquid ethane, not the liquid nitrogen for prompt freezing. Because the conductivity is really good. So the top layer, the top region, we actually get the visual size. And by cryo machining, we actually can getting the visual size samples, which is confirmed by the cryo-TM, the diffraction. The second method, the successful method, is called the hydrogen freezing. By changing the pressure, we actually can freeze or produce visual eyes up to several micrometers or even tens of micrometers. For the prompt freezing, you can only do several hundred nanometers as the maximum thickness for visual eyes. By using hydrogen freezing, we can actually go into up to tens of micrometers, which is quite useful if we are aiming for wholesale imaging. So this is this is to capture there's a surface disk we can use to encapsulate the grid. On top of the grid, we can see the there's also the liquid we actually put that, and also followed by the graphite milling, we can actually produce the visualized needle samples. So we also transfer to APT&M for confirmations, which just appear to be, particularly at the top layers, appear to be vitreous. So the third one is also so that's we developed for the graphing method. So we actually look at and also look at the diffraction pattern for that. Because we cannot doing the atom probe, so we try to simulate the conditions in the APT&M. So basically, we have the liquid samples, then moving to directly freezing in the cryo stage. But they use the liquid nitrogen was used in the APT&M. So we confirmed that's the amorphous state of the ice, and particularly in the top layer, which is useful because that's the regions we actually probe the liquid samples. But interestingly, is in the bottom area, we're actually getting a crystalline structure, crystalline ice close to the bottom. We have some hypotheses, but there's still some not fully understand. There could be the thermal conductivity of graphene is transferred to the top layer. It's effectively transferred, cooling the top layer. It also could be because the region is so small. So we only have 20, 50 nanometers liquid in the tip. So it could be the nucleation of the ice crystal is not very, it has been inhibited because of the size. Yeah. So the second part, so first of all, you actually create the visualize. So second part is we actually spend some time is try to see if we can produce or establish a high throughput. For biological samples, it's always about the statistics. You don't want to just look at it. Eventually, you want to have a high throughput method to look at the multiple samples together. It's still fairly challenging. If you look at the lift out or cryo lift out, I think there's some talks discussed yesterday. It's still a very challenging process. And they also compound the effects, for example, devitrification. So RIV to 106K, we're actually causing problem. And they also could be a mobilization of graphite milling, right? So give you a false information about the icing, right? There are a few ways we actually do. So first is using graphene, we can actually coat the micro tips. So firstly, you produce the tips, and then you can put your liquid samples together with graphene, then coat the multiple samples together. So you can move this one again to move to the atom probe for probing and transfer from ambient to the cryo. So this is from one of the silicon tips. So we do manage to probe several tips on one of the single micro cool pump, and so we didn't move out because of time limit of the probing time, but we proved that it's possible that we can provide multiple samples and do it together. So another thing we actually quite interesting, that's from another project. So we actually could what are the dynamics of the tip, right? So by irradiating the bottom, the root area, not the actual samples, we actually can bend the tip or the needle, right? So this is we start this is called something called a kirigami. It's like a paper cutting. So you can bend the structures. If you have a very thin structure on like a needle structure, you can basically bend it, right? Without a manipulator. It's basically just ion or control the dose of ions. So we think about the way maybe you can use this one as a new method to prepare the samples, right, for both TM and atom probe. So I do have a PhD look at the detailed structures. It turns out that because the ion implantation of the fib is not a uniform distributions, implantations never be a uniform. So for bulk material probably is fine, so just top surface, but for the nanostructures, you cause the instability in the structure. So this will actually cause a certain strain change, which actually can bend the specimen. So that's why we propose we named this as just like a standout method, just compared to the original lift out method. So you can have the ship and just cutting a very normal head. This is fairly standard. Then by cutting away, so it irradiated the root area. So then you can actually use a control dose on the bottom and then stand out a certain specimen. So this can go to 90 degrees. And if you control well, you can actually have a vertical. They can actually, there's some enhancement needed, okay, after that, yeah, just to make sure it's not fractured. So we introduced with the TM group in my university. So we actually did the nanoparticles. So you can deposit the nanoparticle on the top surface. And then you can use the standard method just to move out. So all the process, we didn't use any manipulators. So the gold nanoparticle, which can be successful by TM. So we also attempt the atom probe. It's a little bit embarrassing because we forgot to actually enhance the root area. So there's a certain fracture of that. But we actually believe that actually can be used for atom probe. And also another challenge is we couldn't locate it because the optical microscope in the atom probe is not designed for that. So we're looking for a specimen at 100 nanometer big. So one of the key is the key findings are also the bending process, the ion-induced bending is material independent almost. So almost all the material we try have the same or similar behavior. The second thing is it's also temperature independent. That means we can do the room temperature. We also try to cryo samples. So the dynamics is almost a universal phenomenon. So we think that's probably in the long term we can actually use this as a alternative to the manipulator-based sample preparation. So the TM, the results are already been published. So that's another way we can prepare the nanoparticle samples. You don't have to do the embedding. You basically just this is basically just coated with platinum, so you can have the embedded the nanoparticle stand out and do the TM imaging, and also possibly atom probe imaging. Right. So I added this these slides because yesterday there were some discussions about the GIS-free sample preparation or cryodeposition. So this is one of the recent studies we have performed. So we use the GIS coatings. So the original idea is just like a graphene, we can coat the cryo samples just by the GIS deposition. Then we can actually have a single layers, which is conductive and also transport. So the layer is not strong enough as graphene, and when we transfer, it's actually failed. But we do find that it's possible you can coat a very thin layer. So this is on the right is actually the cryo deposition. So you do have to create a thin layer of the conductive coating just by GIS coating on the cryo deposition, right? Which you can cure by the electron or the ion beams, then move for the atom probability. So the key idea is if you look at the GIS, so I remember someone, James, when discussed this, once they open the GIS, it's all over the place. So, and yes or no, and also no, because the design is in the eccentric height, you actually have the maximum of the deposition rate. You have to move the samples far away from the GIS needle. Okay, once the valve open, because the deposition rate is inversely proportional to the distance or square of the distance. So if you have to keep a certain distance from the GIS needle, you actually can have a controlled deposition rate or cryo deposition rate, which you will be able to actually coat a very thin layer. Okay, we haven't tried the lift out type, but you probably can try if you have a controlled cryo deposition, and also you can cure either with the electron beam and ion beam afterwards. Right. So this is in applied science. If you're interested, you can have a look. Different geometry, but we proved that it's possible to cryo deposition of the ATP compatible component sample. So just as a summary, we actually managed to prove that the VHS needle is possible, it's feasible. And we also propose 3 different type of methods. So this is one of the roadmap we wrote. We believe this can actually give some directions if you in the future want to do a serial imaging with atom probe. For small samples, you can actually using a graphene. So if you have a small molecules like a ribosome, you can actually using a graphene encapsulation method, which will actually you can then move to the onstage cooling, and then you can do the TM or atom probe. And also, if you have a whole cell like mammalian cells, usually in the several micrometers or even bigger, you can use a high pressure freezing method. the in situ, you can actually using the cryo-FIB to create the specimen. Then you can move to the cryo-atom probe. And in this case, you actually need a cryo-transport system. And also the solution, the microcapillary overmicrowave, that's another alternative if you have a small molecules to look at. Right. So just hopefully this will be some of directions or hints if, to enable. But we firmly believe that once we have the bitches, so that means actually the atom probe or cryo-atom probe can actually be used for small molecules or more precise reconstructions without or with a minimum damage of the biological samples. All right. Our summary is so we try to build a laboratory and sample is also the high throughput institute. So our imagine is we can actually do a high throughput method, which can integrate the standout method. Right, we can actually take a small samples from cell or from multiple locations that we can probe by the atom probe. So far we actually did the cell, bacteria, proteins, and because we believe these are the important model systems. But we didn't do, I think, limited this for virus and DNA and RNA, which I think we might have made some mistakes consider the last 2 years. Right? But I think we were actually toward that direction. So I think there are quite a number of groups interested in this. So these are just acknowledge all the PhD students work on this. And just appreciate that work. They really demonstrate a can-do attitude, which no one has explored before. So some of the reference we have, so if you're interested, you can have a look. All right, acknowledge again. For example, the Deakin University, so Ross, Adam, Florent, they have spent quite some time with us. Also, Professor Gang Xia and so helps with the nanoparticle. So it's quite interesting. We transfer the samples into Nanjing for probing, and also different people from molecular medicine and molecular engineering. All right. So that's the end. I'm happy to take any questions if you have.
Thank you, Jing. Wonderful talk. It's really exciting to see how innovative you guys are really pushing the limits of what one could do with the limited, without having to do a lift out. Some of the things I've been trying to do is a lift out, which is, as you know, quite challenging. Right. So
yeah, everyone hates lift out.
Yes, absolutely.
Then you think about the cryo lift out.
Yes, right. So we got time for a couple questions. It looks like on the chat there's been some questions, but Ross has been so kind to kind of field them. But if anybody has any questions that they would want to maybe speak up now.
Yeah. Thanks to Jun for very interesting talks. I was amazed about the without lift manipulator to do the sample preparations, and I found you select the material combination is interesting because you want to investigate the gold nanoparticles, but you use substrate is copper. Then you deposit layer is PET. I think PET may have good match with gold, but maybe not a good match with copper because the field difference between the two materials is too big. So that will create the trajectory overlaps. Then it will, I think, influence your measurement. Maybe if you select the PET matrix with the gold particles, then you deposit PET. Maybe make it easy to run. That's my assumption.
Yeah, that's a good point. The reason is that was the first attempt, so we just want to have a quick material to do that test. So the PET basically we can actually deposit by the GIS. You can have a different matrix prepared on the flat surface that you can actually stand out from that. That should not be a problem. So it doesn't affect that.
Yeah, I think also it's important to consider the field difference between the materials you choose. Yeah, that's good.
Yeah,
very innovative.
Long term. Yeah, you think about the long term is the probing part. Yes, we didn't think about that when we actually do the testing.
Okay. Okay, that's good. Thank you.
Thank you. We'll take one more question. It's just so interesting. Tong Li has her hand up here.
Yeah. Hi, Dan. Thank you. Hi, Jing. Thanks for the talk. You mentioned that you have some methods to like image larger volume of water. Is this the one like you cut in the trench and then put in the plunge freezing? Or can you please elaborate like what exactly you mean? Like you can image larger amount of water molecules?
You mean when you say large volume, is that being said?
So what I mean is like by the graphene coating, you essentially have a very thin layer of water, and later on you said you found out some better method to have more.
Yeah, we did some testing. So it's about the so there's some parameters you can tune. Particularly for the coating, there's a so there's a speed that you can actually control. So you want to actually lower the graphene towards the. So I think that's the best way to do is the animation. So the speed is actually quite quite critical. So usually we found that the slower the speed, the more liquid you can trap.
Okay, and I'm wondering like for the one like you having cutting trench and you put a plunge freezing and you have the liquid in the center of this cavity, and then afterwards you do the cryofab on it, and the thing is that you don't have any connection between the liquid and also the gaps, and after you do the annular milling, and essentially you have a freestanding of the frozen liquid part with the matrix, and did you have a problem with running this material?
That's good actually. But this one we haven't actually tested the atom probe, but we tested APT&M, so it looks like strong enough. So in the bottom you probably have to make a little bit roughen. So we created the so it's actually a good question. So this region you actually have to make it rough. It's not a smooth area. So it's more like a nanoporous. So which give a good adhesion of your liquid to the solid.
Okay.
Yeah.
All right. Thank you, Jing.
So the interface is quite quick. Yes, that's an excellent question.
Okay.
Thank you, Jing. I know, Rob, you got your hand up there, but in the interest of time here, not putting us too far back, if you don't mind, you can put it in the chat there, and Jing would be able to answer it, but we'll just move on from here.
Right.
Thank you, Jing.
Yeah, thanks.
Okay, so our next speaker is from Dr. Sandra Taylor from Pacific Northwest National Laboratory, and she'll be talking about analysis of complex protein mineral interfaces in vitro. Go ahead, Sandy. Thank you. Looks like it says it's sharing your screen, Sandy, but I don't think we're seeing it yet. And if you're trying to speak, we haven't heard you yet. Okay, we can see your camera.
Hello.
Okay, we can hear you now. Thank you.
Hello.
We can hear you.
Can you hear me?
Yes.
Oh, okay. Okay.
We can hear you.
Can you see my screen?
Yes.
Okay, great. Thank you, Danny, and to the conference organizers for putting on this event. My name is Sandy Taylor. I'm a scientist at Pacific Northwest National Labs in Richland, Washington. And today I'd like to talk about some work that we've been doing to utilizing atom probe tomography to understand complex protein mineral interfaces of relevance to understanding biomineralization mechanisms. So, and so the motivation for this study is to understand how organics interact with mineral phases and what their role is in biomineralization. And as a fascinating example of this, tooth formation is intimately linked to the interaction of the protein amelogenin with evolving calcium phosphate phases, where the speculated mechanism is that at the onset of biomineralization, calcium and phosphate ions aggregate to form amorphous calcium phosphate clusters, and amelogenin, represented by these gray spheres, promotes their stability by what's speculated to absorb onto these clusters. The amelogenin also facilitates the assembly of the ACP clusters into these thin ribbon-like structures that orient themselves and eventually weave into hydroxyapatite crystals that are elongated, and this is what forms enamel. Additionally, deviations in how the amelogenin interacts with the mineral phase can lead to very different results in how enamel forms, where under normal conditions, the final enamel product has the protein removed, and that leads to nice teeth. But in other instances where the protein perhaps there's a higher protein content in your enamel, this is thought to lead to defective enamel or conditions called amelogenesis imperfecta. And so you can see just from this example of tooth enamel formation how significant the interaction of organics with the mineral phases is during biomineralization. And so to understand these biomineralization mechanisms, we need to get direct observations of how proteins are interacting with minerals at specific sites, particularly during the early stages of crystal growth. And so, as you're probably well aware of, APT has been applied to the analysis of bulk mature biomaterials like enamel, where Dirk Joster's group, for instance, has highlighted how nanoscale chemical heterogeneities occur within enamel, and possibly you can infer some mineralization processes from these observations. However, as I showed in the previous slide, the interaction of amelogenin with these calcium phosphate phases is really critical during the early stages of mineralization. And so it's important to study these reactions in vitro to be able to follow the roles of protein during the evolution of these mineral phases. But there are several challenges that need to be overcome that include preparing specimens, particularly these nanoparticles of ACP or HAP that form in aggregate, as well as interpreting the complex protein mineral interfaces that arise from these aggregated structures. And additionally, we need to have a reliable way to identify the protein signatures. So this involves having unique protein signatures that we can use. And so the aim and approach for this study was to be able to resolve protein distributions involved in the mineralization of hydroxyapatite in vitro by atom probe tomography, where we built on our previous studies looking at crystal growth mechanisms of iron oxides, where the general idea was that we would take these hydroxyapatite systems, which in this case are nanoparticles, but we could prepare them using techniques similar to what we've discussed before into APT needles, where the nanoparticles are embedded within a chromium coating, and then interpret the mass spectra to reconstruct these more complex aggregated structures. And part of this, there were two parts of this research that were required to resolve the protein distribution, where the first task involved analyzing a model protein mineral interface by APT, where in this case, amelogenin is absorbed onto these 100 hydroxyapatite surfaces as confirmed by AFM. And so then when we analyze this by APT, we're looking for what unique signatures can belong to the protein. And then after we figured out what the protein signatures were, we applied atom probe tomography to probe the protein distribution within these mineralized hydroxyapatite nanoparticles where the protein distribution is unknown. For instance, it could be incorporated inside the nanoparticles or associated between particles. So our first task involved deducing the protein signature from these model systems with amelogenin adsorbed onto the hydroxyapatite surface. For these samples, we prepared tips such that the mineral phase is along the length of the entire tip. And also these specimens were coated with chromium to protect the adsorbed protein at the surface. And what we find is that we're able to capture different signatures belonging to the different components we have in our system, where, for instance, chromium coating is denoted by the chromium 2+ species. Hydroxyapatite belongs to the Ca2+ ionic species. And we're picking up organic signatures, where in this particular instance, I'm highlighting the CO2 1+ species, which interestingly seems to be localized at the hydroxyapatite surface. And so if we probe this chromium hydroxyapatite interface further and specifically look at the organic species that we're picking up, we can see, for instance, that certain signatures like carbon 1+ species aren't strongly associated with the hydroxyapatite surface, whereas some other species like CO2 1+ are pretty strongly associated with the hydroxyapatite surface. So based on these spatial trends, we're able to say what species can be used to resolve the protein signature, which in this case seems to be these CO2 1+, as well as CO 1+ species, as denoted by this concentration profile across this particular region, where you see CO and CO2+ species localized on the apatite surface. And so with this knowledge of how we can, of how to identify the protein signature, we applied this technique to probe the protein distribution in this amelogenin mineralized hydroxyapatite system, where in general, these nanoparticles were prepared into tips, where the nanoparticles are located along the tip length. And again, this was based on techniques we had developed previously for iron oxide nanoparticles. And what we find are these unique morphologies belonging to the hydroxyapatite, as denoted by the Ca2+ species. And similarly, we're picking up protein signatures, again, the CO2 1+, and those seem to, again, be correlated to the hydroxyapatite particles. If we look at one of these particles or particulates in cross-section, what we see are the red atoms are the CO2 1+ ions. And so you can see that they're heterogeneously distributed across this particulate, where there's some localized in this junction between two particles. So that's this Y-shaped region denoted here. And then you can also see that there's some ions associated within the particulate overlapping with the calcium 2+ signature. And so this is interesting because it raises the question as to how to interpret how the protein is associated with the mineral phase. Where above the junction, we again can see that seems to be between two different particles, but within the junction, could this be interpreted to be incorporated within the particulate or between particles? And so if we further utilize these cross-sectional analyses by APT, we can determine that the protein appears to be trapped between particles, which likely occurred during particle fusion. And so to highlight these analyses, we can show this particular particulate in cross-section where at certain depths, so for instance, X1, you see that there is no distinct particles that could be determined, but moving in cross-section through this particulate, we can start to infer particle boundaries, where in this case, at depth X2, we're resolving what appear to be at least 3 different particles, and can see that with moving through the cross-section that these particles appear to be fusing. And so that explains how protein can be entrapped between particles during particle fusion. And so these observations are unique because there's few techniques being able to capture the protein distribution relative to the mineral phases. So for instance, transmission electron microscopy has issues resolving this due to low contrast. And similarly, APT, while it can resolve these organic signatures, this is the first study to do it systematically, where we're able to follow the protein relative to the mineral phase and determine certain mechanisms like particle fusion trapping the protein. And so this is of interest to understanding biomineralization mechanisms, where we can do additional in vitro experiments to understand the evolution of these mineral phases relative to the protein. And this technique can also be more broadly applied to understand mesoscale crystal growth and assembly, where there's plenty of interesting things to understand with how particles aggregate, and perhaps this technique can be used to understand particle boundaries and whether surfactants or other things play a role in how they aggregate. And so with that, I would like to thank my collaborators on this project, particularly Arun Devaraj for his contributions to the APT analysis, as well as Jack Grimm. And I would also like to acknowledge the National Institute of Health, particularly the Dental and Craniofacial Research Department, for supporting this research, as well as the Environmental and Molecular Sciences Laboratory at Pacific Northwest National Labs for letting us use their equipment. And so with that, I am happy to take any questions.
Thank you, Sandy. Can you hear us, Sandy? Can you hear us? Yes, hello? I don't think Sandy can hear us. So with that,
I can't hear you.
I know. With that in mind, if we have any questions, so we can maybe catch up on time, why don't we use the chat to share your questions or comments or praises for Sandy, and then we'll just move on from there. So Sandy, we're gonna.
I can't hear for some reason.
Okay, let's see if Sandy sees that. Oh
man.
Can you see that? All right. We'll queue up Natalie here. For those who had joined late, unfortunately, John is unable to deliver his talk, but Gong Sha will be presenting, or someone from his group will be presenting in his place, just to keep this program moving here. So Gong, if you want to maybe take over.
Yes. Thanks. I think, yes, I just want to take this time slot to, can you see my slides?
Yes, we can see everything.
Okay, that's good. Okay, so I need to change into broadcast mode. Okay, I just want to take this opportunity to express our thanks. First, thank all of you attending this conference, and it's over the last 10 months we prepared this conference, and we would like to thank the International Field Emissions Steering Committees who gave the guidance. I also would like to thank Nanjing University of Science Technology, AMETEC Kamika Shanghai, and Caishi Shanghai to provide the financial support for this conference, as well as the National Center for International Collaboration of Nano and Micro Materials and Technology Center. So really, it is those sponsors and the support from the different organizations make this conference possible. So there was a hiccup at the beginning, but later on the whole running is pretty smooth. So I certainly enjoyed the conference. I hope you all also enjoyed the conference. All the presentation and the talks is really in high qualities. So I also would like to thank local organization committee members like Professor Yuan Wu from University of Science Technology Beijing, as well Rong Hu from Yangtze Delta Region Institute of Advanced Materials, and Flau Virgo and from Jinan University, as well Shen Baojing from Nanjing University of Science Technology, as well as Tianyu Deng from Nanjing University of Science Technology, to do a lot of corresponding work, as well as helping to review the programs and also make review all the abstracts and make up these programs. Thank you all for your excellent contributions. So with this opportunity, I also would like to thank those research students of my group who work behind the scene to make this this conference possible to run smoothly, and they working on to record the talks and release all your talks on the YouTube under your permission. There are some talks due to unpublished data, it is not recorded. So I also would like to thank Dian Jiao. He is a master student in my group. He helped to set up the conference website and make it functional and to receive all the abstracts and posters as well. So thank his hard works. So here I also would like to thank for the respected guests to join from the Nanjing University of Science Technology to join the open ceremony. Unfortunately, we experienced to organize this online conference, and the machines have a problem on that day. So you didn't see the image, or you didn't hear any of my speech, my talks, my songs. So here is a picture of all the people who joined the open ceremony to support this international conference. So I also would like to thank all the speakers, invited speakers, to give the excellent talk at this APT&M 2022. It is your contributions make the conference with great success, and there are so many important informations and new research progress has been shared at this conference. And I just take this image to represent all the invited talks, also the speakers. So in this conference, we have the 9 invited talks, about 80 regular talks, over 20 poster presentations, and there are also there are 5 media competition presentations. And we have over 200 people registered and attended this international conference, make the information well spread and well received. Thank you all for spending your time and working on those wonderful presentations and attending this conference. So on behalf of local organization committees I would and my research teams thank you all for your excellent contributions and make this conference successful. So I also would like to thank your great contributions and see you at the Atom Probe Microscopy 2022. So this is a short presentation from me to fill in the spot.
Thank you, Gong. We'll send a virtual applause. So thank you very much. Coming from someone, been involved with organizing a meeting of this size, right? One of these virtually. We really appreciate all the hard work you and your team have put over there into this wonderful session, and very grateful for all the speakers who gave these wonderful talks, and appreciate you guys' hard work on this.
Okay, thank you.
Okay, Gang.
Yeah.
And thanks for filling in too on a short notice. All right, so the last session of this, or the last talk of this session, is by Kyung-Seong Young from KAIST, and he'll be talking about atom probe tomography of dielectric barium titanate for multi-layer ceramic capacitors, combining metal encapsulation with heat treatment. And this will be the last talk of the session, and then there will be a break to switch between sessions. So take it away. Thank you.
Yeah, thank you for introduction. Can you hear me?
Yes, we can hear you.
Yeah, okay, I will start. Hello, my name is Kyu-Sung, a PhD student in KAIST. Today, I will present about the APT of dielectric BTO layer in multi-layer ceramic capacitors by combining metal encapsulation with heat treatment. Before we go any further, I will introduce what is the MLCC and why we need APT analysis of the dielectric layer. MLCC is the capacitor consisting of multiple stacking layers of internal electrodes and the dielectric layer. Generally, nickel and BaTiO3 have been used as an internal electrodes and dielectric layer, respectively. The MLCC offers many advantages to electronic devices. For example, it controls the current flow in the device, then it can remove the noise, malfunction, and electromagnetic interference between multiple components. So it's one of the key components in the electronic devices. There is various size of capacitance depending on its application, like automobile, computer, smartphone, and so on. And in the MLCC, many kinds of additives are doped, mainly in the dielectric layer, to fine-tune the performance of the MLCC. These are representative additives doped in BTO layer and their roles. These additives have a great influence on properties, even if they're trace amounts. So it is really important to find the link between the location and actual concentration of additives with resulting properties for designing advanced MLCC. However, existing analytical techniques are not suitable for additive analysis because they do not provide sufficient detection sensitivity and a spatial resolution at the same time. In this situation, APT is the potential technique for this purpose due to its superior and equal detection sensitivity for every element and great spatial resolution. The SEM image shows the surface of the MLCC we used. Consists of alternate decal BTO layer with the 300 nanometer of average grain size. We fabricated every APT specimen from the right center region of BTO layer to minimize the inclusion of diffused nickel from the electrodes because MLCC was made by high temperature centering about 1200 degrees Celsius. And also, every tube was fabricated with similar shape to figure out the exact difference between different sample preparation methods. And in our sample, manganese, vanadium, aluminum, and magnesium were doped in the BTO layer with less than 0.5 atomic percent. So our purpose is analyzing these four elements. First, we try to analyze as fabricated BTO without any preparation. We tried the analysis with two different ranges of laser energy. When the laser energy is below 150 picojoule, premature fracture occurred, and burst evaporation of Ba, barium, was identified. Although the mass spectrum shows clear peaks, the composition of this sample is severely deviated from the nominal composition BaTiO3. In contrast, when the laser pulse energy is above 250 picojoule, the burst evaporation of barium was suppressed, But now, severe thermal tail appeared. Therefore, regardless of the laser pulse energy, we cannot analyze BTO well with the as-fabricated state. And then, our first strategy to solve this problem was metal encapsulation on the final milled tips. In previous papers, it was reported that the metallic coating increases the conductivity of the sample, enabling a uniform and stable analysis of oxides. And in that paper, silver was reported as the best coating material due to its high conductivity. Then we first conducted the silver encapsulation by DC sputtering. However, as you see here, silver coating didn't improve the APT result. First evaporation of barium was still observed, and thermal tail was still severe, and the composition was greatly deviating from the nominal value. This is because the evaporation field of silver was lower than that of BTO, and evaporation was not uniform as shown in the detection rate history. And the sum of the squared residuals are very high. Then we select the coating materials considering two criteria. One, the material should have a similar evaporation field with BTO. And second, it should have a strong adhesion on the BTO surface. Of course, we cannot figure out the exact evaporation field of a BATiO3. So we assume that the BTO evaporation field of BTO is higher than general value of metals. So we intended to select the coating material among the 7 with the highest evaporation field among metals, according to the image hump model. And next, adhesion on the BTO surface was roughly estimated by the surface energy value in this paper, because in general, the higher the surface energy, the stronger the adhesion strength. So finally, we selected tungsten as a next coating material. This is the result of tungsten-coated specimen. A fairly uniform BTO layer was obtained at the top region. Also, surprisingly, a large amount of tungsten was observed not only in the topmost layer, but also in the middle region. If we enlarge this part, it is observed that tungsten is at the edge part as shown on the right side. It is presumed that the tungsten at the edge part of the tip remains during the APT analysis and evaporates later because of its high evaporation field of tungsten. Now, the result shows the thermal tail of the mass spectrum was significantly suppressed, allowing the analysis of trace additives. And also, the composition is quite well matched with a certain amount of analysis quality could be obtained only with the tungsten coating, but still some burst evaporation occurs, and evaporation were slightly unstable during the analysis. Therefore, we added the new process to obtain better APT analysis data here. That's the heat treatment. The heat treatment was applied to mainly control a piezoelectricity of BTO. Piezoelectricity is the interchange between electric field and the shape deformation. Because high electric field is applied to the specimen during APT analysis, for materials with high piezoelectricity, this may lead to the premature mechanical failure. The piezoelectricity decreases through heat treatment. This is called aging degradation, and the degradation increases as the heat treatment temperature increases. We carried out the annealing for 2 hours at twice of the Curie temperature at which BATiO3 loses its piezoelectricity. It is 240 degrees Celsius, and we expect heat treatment may also increase the adhesion of coating material and relax the internal stress and improving the analyzing quality. This is a representative APT results of the heat-treated specimen after tungsten coating. Compared with the tungsten coated specimen, the analytical yield was generally increased, and the analysis shown in the detection rate history was much more stable than before. Also, the composition is matched well with the nominal composition. Further, comparing the analytical yield and the average detected number of BTO atoms in each method, it can be seen that tungsten coating and heat treatment improve the analytical result respectively. So by applying this metal encapsulation with the heat treatment, we can analyze the distribution and local concentration of every additives in the BTO layer. In addition, there are diffuse nickel in the APT tips. Even we fabricate the APT tips from the right center region of the BTO layer. Also, the measured concentration of these additives was well matched with the nominal concentration. It proves the better APT analytical results of ours. So in summary, tungsten coating shows the better APT results than as fabricated states due to its high evaporation field and strong adhesion on the BTO surface. And by combining the heat treatment with the tungsten coating, we can further improve the analytical stability and yield of the BTO analysis. Finally, we can investigate the three-dimensional distribution and concentration of additives in BATIOS3 layer of MLCC by using this tungsten coating and heat treatment approach. Thank you for listening.
Thank you, Kyo-sung.
Yeah.
Thank you for that wonderful talk. Is there any questions from our audience there? Anybody want to raise their hand or kind of speak up? Any questions for Kyo-sung?
I asked a question in the chat, but
Oh, did you? Oh,
yeah,
yep.
that's okay. I can also speak up now. So are you not introducing some redistribution of these impurities by the heat treatment itself? Are you expecting that the diffusion is going to be very slow at 200 C?
Yeah. That's the point to be concerned about. Actually, but we assume that diffusion can be ignored in that case because the MLCC was already fabricated under very high temperature for sintering, and yeah, maybe we need further improvements for proving that, if that matters. Sure. Yeah.
Okay, thank you.
And I had a question about the tungsten distribution before and after heat treatment. Before heat treatment, you showed instead of just being on the outside, it was all throughout, right?
Yeah.
And now with after the heat treatment, it's a different distribution. Can you talk about that a little bit? What's going on?
Yeah. Oh, sorry. I closed my. Yeah, I think it can be heard by this scenario. At the first stage of the analysis, the top region of the tungsten coating was evaporated, and then the tungsten at the edge part is remained, and then BTO evaporates further, then edge part of the tungsten at the edge part evaporates later. That's why we find this weird shape And one more interesting thing is we also have got the results which tungsten coating was only only located at the topmost region. But in that case, we investigate the severe thermal tail at the mass spectrum, and also the evaporation is unstable. I think because for getting better results, tungsten should be remained at the bottom region of the APT tips for stabilize the conductivity and also mechanical strengths.
Okay, thank you. Yeah, Pat has a very true comment. If you want to read it there, it's a BTO. It's a very challenging material, period. And so kudos to you for collecting data at all, just because it's so challenging to work with, right? Such a challenging material.
Yeah.
Is there any other questions from the audience? And if not, then that'll conclude our session here. Thank you, Kyo-sung. I appreciate your time and presenting your research to us. And with that, we'll end our session. We'll take a break and return back after 9:50 this morning. So thank you, everybody.
In today's challenging environment, scientists and engineers need to accelerate discovery processes. CAMECA offers unique, high-performance analytical instruments to help them unveil the secrets of life and materials at the micro, nano, and even the atomic scale. Founded near Paris in 1929, CAMECA rapidly established its name by pioneering first electron probe microanalysis, followed by secondary ion mass spectrometry, and more recently, atom probe tomography. Ever since, we've maintained our R&D investments at their highest level and partnered with leading academic institutions in order to explore new techniques and technologies. Today, CAMECA is part of the Materials Analysis Division of AMETEK, a global manufacturer of electronic instruments and electromechanical products. We have locations all around the world and strive to expand our reach to new geographical frontiers in order to foster emerging scientific players. Our state-of-the-art production facilities in France and the US allow our experts to develop the most sophisticated microanalytical tools used for research and process control applications in materials, semiconductors, geology, environmental and life sciences. Huge investments are made worldwide towards the development of stronger, lighter and more durable materials for transportation, energy production, aerospace and defense, and consumer products. Materials scientists rely on CAMECA instruments not only to gain a deeper understanding of the properties of materials, but also to predict their performance in real world. CAMECA also accompanies semiconductor manufacturers as they explore the boundaries of physics. Our metrology tools enable the production of latest generation electronic devices, contributing to a world where communication is faster and more reliable. From understanding the microstructures of rocks and the genesis of the solar system to revealing water and soil pollution processes, CAMECA provides the tools for writing the history of the universe and creating a safer environment. Offering novel and powerful instruments for studying intra- and transcellular metabolic pathways, DNA expression, virus penetration, and drug localization, CAMICA enables important medical advancements. Thanks to such a wide spectrum of applications, our instruments have been adopted by top-ranking academic and research institutions, as well as major industrial corporations all over the world. Their satisfaction and success are our main focus. The expertise and passion of our teams will enable us to further push the limits of microanalytical instrumentation and help our customers reach the highest performance in their specialized fields. CAMICA, Science and Metrology Solutions.
Close your eyes. What do you see? Do you see yourself, the path in front of you, the next step? Do you see your ambition, the cutting-edge approach that opens new dimensions in medicine, the biggest miniaturization that lays the foundation for the digital revolution, the holistic perspective that transforms humanity for good, the progressive vision that changes everything, the way you see the world, the way you capture moments, the way you transcend knowledge, the way you define precision and productivity, the way you live, move, love, heal, think, are. Open your eyes. Can you see it? Together, we are challenging the limits of imagination. For those who see beyond. Zeiss. Seeing beyond.
Okay, Anoop, please be ready. We're starting maybe 3 minutes. Mm. Mm. No, but can you speak a little bit? Just make sure that.
Hello,
Oh, yeah,
am I audible?
Yeah, I can hear you.
Okay.
Great. All right. Sorry, 50. Hello everyone. So I'm happy to chair this 12th technical session. We don't have an invited speaker for this session, but we do have 4 speakers to give the talk. The first speaker is Anup Sharma, who's from Indian Institute of Technology in Bombay. He's actually a joint PhD student under the supervision by me and also Professor Deepak Mala. So he brings a rich experience in the laser science. So we actually ask he's actually working on how to model the laser interactions with the atom probe sample preparation and also the probing. Right. Anup, you can start.
Okay, thank you for the introduction. Hello everyone, my name is Anup Sharma. I'm a PhD student in a joint program between Indian Institute of Technology Bombay and Monash University in Melbourne. So I'll be presenting my work on the laser machining for APT specimen preparation, majorly to reduce the overall sample preparation time taken in the APT sample preparation. So we know the basic requirements. We all know the basic requirements that are for the major methods that are required. So we need site-specific specimen so that the cross section is visible. We also want the preparation time to be low and with a certain degree of ease of operation, and also we want the method to be damage free. So, if we talk about the existing method, yes, we know about electropolishing. It's been there for decades, but it's specific to conducting materials. One of the most widespread methods is to use focus and beam machining. However, we all know that it has a comparatively low material removal rate, and hence one of the new things that people are trying is to have a coarse machining process prior to FIB in order to reduce the overall load that FIB has and decrease the sample preparation time. So one of these method is to use a laser prior to FIB and reduce the overall sample preparation time. So let us have a look at the recent attempts that people have made in this direction. One of the recent one is I'll just share the pointer. Okay, so one of the recent one is uh, where people use a grinding wheel, silicon carbide grinding wheel, to create a ribbon-like samples initially, and then perform manual milling with FIB to reduce the size. Sure, sure, the sample preparation time was low, but I think there could be it could be potentially damaging for some materials. Secondly, yes, people have tried with lasers, with femtosecond lasers, and with also with picosecond lasers. This is the new laser fib system that Zeiss has been promoting, and the other one is a picosecond pulse laser. So yes, there have been attempts on laser, but however, I think a more detailed and more fundamental approach is missing. And in order to characterize the sample, and also in order to identify the heat penetration inside the sample during the laser preparation time. So, looking at the current attempts or the recent attempts in this direction and the overall requirements of the process, we decided to model to create the objectives something like this. First, the objective was to model the overall heating process during the laser machining process, and we have selected two materials, silicon and aluminum. Second was to evaluate from the model itself, from the simulation itself, evaluate the region which experiences temperature, the region which goes higher than the recrystallization temperature. So and that would be characterized as damaged. Third would be to prepare specific micropillars with the specification taken, with the process parameters taken from the simulation. And last, to characterize the micropillars and examine the pillars to check and measure the extent of damage that is there. So we start with the simulation. We model the laser heating of silicon aluminum and predict the extent of heat affected zone, which we have called HEZ. So then we go on to the experimental part and perform the machining with a picosecond laser, 3D microfib, and then we initially used laser milling for the thing, and then used FIB cleaning to clear off the visible damage. The final characterization was done using EBSD for mapping the microstructures of the top of the micropillars. So this is a brief description of the model that we have used. So what we've tried to do is try to create a single pulse laser heating model using a finite difference method and explicit scheme. We developed we have an in-house developed Python code for this, and if you could see on the image on top right. So what we are trying to do is, if this is if you take this to be an annular motion of a laser beam, so we are trying to gauge this heat affected zone. So we know that if we are trying to create a pillar, so there would be a significant heat affected zone if we are using laser. So if we manage the size of the pillar and process parameters appropriately, we believe that we can have we will definitely have some heat affected zone, but we will certainly be having some central region which would be preserved, which would be suitable for further FIB operations for creating the APT samples. So these are the parameters that we have used for the simulations. We varied the pulse energy from the lowest of 60 microjoules, and that was capable in the machine, up till 250 microjoules. The laser beam diameter, the spot diameter at full width half maximum was around 12 micrometers. The pulse duration, as I said, it's a picosecond laser machine. It's around 490 picoseconds. The mesh size, the grid size is 50 nanometers. The wavelength is 532 nanometers of the incoming laser beam. So these are the simulation results from the model that we had. If you could see on both the right and left hand side image, the red dotted line is the recrystallization temperature for both of these, and the region which is which experiences temperature lower than this is characterized as safe. This is the region which is not experiencing recrystallization temperature, and hence it would be free from damage. So this is the distance. If we mention what we say the distance from the laser beam is, this is what we call which we have characterized as distance from the laser beam. This is the laser spot, the radius of it, and distance from it is here mentioned on the x-axis. So in silicon, we say that with the lowest pulse energy, what we have is around 3 micron region from the laser beam experiences temperature which are greater than recrystallization. And for aluminium, we have around 6 micron with the lowest pulse energy, since since and the conductivity is much higher in aluminium, so we have slightly higher heat penetration inside the aluminium sample. So if we going ahead, we use the same parameters of lowest pulse energies for silicon and aluminum, and perform the experiments for creating the micropillars. So for both silicon and aluminum, and these are the parameters consistent with the machine. We use a 3D micromag micropillar machine, and the overall laser machining time was less than 20 minutes, and so we know that it is a much quicker method to use as a coarse machining process prior to FIB. We created the micropillars, and when we examined with SEM, we saw that there was some visible amorphized and oxidized region outside. So we cleared it off using an FIB machining, and we observed the central part later on with SEM. So these are the SEM images for the samples. The top one are the as machined micropillars directly from the laser machining setup. And you can see that the white layer which is generally amorphized and oxidized layer. When we cleaned it off using FIB, we could see that the central region, the central pillar, was found to be free of any surface damage, and there were no pores or micro pores or nano cracks over there. So the surface deformities were not found with SEM. So we went ahead and performed microstructure characterization of the top of the pillars. These top were scanned with EBSDs. Then if you see the top images on both sides, left and right hand side, the left hand side is for silicon, the right hand side is for aluminum. We can see with the color map that the central region is preserved and is intact and is suitable for APT sample preparation. The periphery in silicon, since it was much smaller diameter, yes, the periphery is damaged, but the central region, as we predicted, is suitable for APT sample preparation. We also measured the degree of misorientation of the grain boundaries along the line as seen on the images, along this line and this line, and we found that the overall degree of misorientation in the center was less than 1 degrees, and which is acceptable or which is most of the time case in the unprocessed samples as well.
I know for 3 minutes left.
Okay, yes, I'll wrap it up. So as the simulation results were consistent with the experiments for the two materials, that is aluminum and silicon, we also applied it to other materials, other common materials, with the same procedure. we obtained the temperature data and evaluated the minimum value of safe diameter for these materials. It could be seen on the top right image. What we mean by safe diameter, we have tried to depict in the bottom right image. We can see that let's take R to be the diameter of the laser beam. Y would be the distance of the heat affected zone of the pillar, and X would be the radius of the center required by the user. It depends on the factor of safety the user wants to take. So if we perform the simulations, we could get Y from the simulation, and R we can have from the machine itself. We know the machine has a particular laser spot diameter and laser spot diameter, and so we could get this the value of safe diameter from the simulation if we perform such an analysis. So from the image we can see that the maximum diameter that we were having was for aluminum of around 24 microns. So let us have a look at the conclusions. If you would like to conclude that the depth of heat penetration we obtained with the numerical model, and it was consistent with the experiments. We have evaluated the minimum value of temperature. With characterization, we saw that the center region was found safe for further APT sample preparation. For silicon, the minimum diameter was somewhere around 10. For aluminum, it was 28. And we found that picosecond pulse laser they can provide a good balance of economic feasibility with low thermal damage if we keep the process parameters properly. Regarding the future scope, I would say that yes, we have to perform atom probe tomography for such samples, laser process samples, and then compare with purely FIB operated process samples, and then maybe go ahead with creating an empirical formula for getting the minimum value of safe diameter, which could be used across different materials, and also validate the simulation for some other materials as well. So that's it from my side. Thank you.
Yeah, thanks, Anup. We might be able to take one. I think it's already 5. So if you have a question, probably you can put in the chat box. So we can move to the next speaker, the Yang. Yang Kong, and you can start your presentation. Ben, Mappa, are you there? You can start your presentation.
Okay.
Right. You can share the slides. Yeah. And now I can hear you. So yeah, I leave it to you.
Can you hear me?
Yes. Yes, please.
Okay. Okay. Good morning, everyone. My name is Man Feng from Nanjing University of Science and Technology. And the topic of my report today is microstructure evolution and element distribution of binary aluminum, magnesium, silicon copper alloys present my high pressure torsion. I will introduce the following contents. The first part, introduction. HPT is an interesting form of severe plastic deformation. In recent years, researchers find the HPT come from ultra-fine-grained structures and redistribution of solute elements in the alloy, such as grain boundary segregation, solute clusters, and precipitation, resulting in excellent mechanical properties. However, most studies focus on the interaction of solute atoms in complex aluminum alloys systems, but the element revolutions of single solute atoms is deficient. And therefore, we selected 3 temperature typical binary aluminum alloys for the study, namely typical deformation, hardened aluminum magnesium alloy, and typical cost aluminum silicon alloy, and precipitated hardened aluminum alloy. Moreover, magnesium, silicon, copper atoms are also the main elements of commonly used complex systems. And therefore, this work we studied the microstructure, evolution, and element distribution of three binary alloys with a mass percentage of 1 under HPT. And the three alloys were homogenized and solute temperature. And micro hardness of the samples were tested by Vickers micro hardness tester. The microstructure of samples were characterized by EBSD, TKD, TEM, and APT. This is the microstructure and the solute redistribution of samples before HPT deformation. Figure A2C, the EBSD diagram of three binary alloys before HPT deformation. We can see the microstructures are congruent. Figure D2F, the atomic distribution of three alloys. We can see the solute atoms of three alloys are uniformly distributed, which is also consistent with the nearest number distance analysis. Sorry. Yeah. This original micros hardness of three binary aluminum alloys. Figure A2C, the micros hardness variation of three binary alloys with equivalent stress and different revolutions. We can see with the increase of strain, the micro hardness of aluminum, magnesium, copper aluminum, magnesium, copper alloys gradually increase and finally reach the saturation value. However, the micros hardness of aluminum, silicon, alloy so far and high stress. We used the TKD to test the grain size of samples after HPT and different revolutions. To better understand the variation trees of microstructure, we plotted the grain size and grain size values of three alloys and different revolutions. We can see with the increase of strain, the grain size of aluminum, magnesium, copper alloys gradually refined, while the grain size of aluminum, silicon, copper gradually coarsened. And then we used the TEM or STM to test the precipitation of samples after HPT and different revolutions. In the TEM image, we can find there's no precipitated phase in aluminum magnesium alloy after HPT. But in the STM diagram of aluminum, silicon, copper alloys with different revolutions from D to I, we can see the obvious precipitated phase under and green boundary and within grains. This is the APT data of aluminum magnesium alloys after HPT deformation and different revolutions. In the APT data of 1 and 5 revolutions, we can see they consist of 2 grains and magnesium depletion zones. We find no segregation at GB1, while weak segregation GB2 and GB3. In the APT data of 10 revolutions, we collected more complex data. There's no segregation at GB4, and magnesium depletion zones near the green boundary, but obvious segregation at GB5 and 2GB8. This is the APT data of aluminum silicon alloy after HPT deformation and different revolutions. In the APT data of 1 revolution, we can see the silicon depletion zones in the single grain. The silicon concentration in the matrix and silicon depletion zones concentration are 0.6 and 0.08 atomic percentage, respectively. In other words, silicon atoms are not uniformly distributed in the matrix. In APT data of 5 and 10 revolutions, we collected 2 grains, and no segregation and segregation were found at green boundary. However, poor silicon particles found here, and the silicon segregation and the dislocation. This is the APT data of aluminum copper alloys after HPT and different revolutions. The obvious segregation and the green boundary and dislocation. Moreover, in the APT data of 10 revolutions, we've collected the precipitated phase. And the program favor the copper concentration in the precipitated phase is about 30 atomic percentage. This is a schematic diagram of the distribution characteristic of solute atoms is 3 binary alloys before and after HPT deformation. We can see the aluminum, copper, magnesium, silicon atoms is segregation, partial segregation, and nano segregation and green boundaries, respectively. And magnesium atoms forms magnesium enrichment zones with about 30 to 40 atomic percentage, and silicon copper atoms forms precipitated phase. Moreover, we plastic the solute atoms concentration in green matrix of 3 alloys and different revolutions with the increase of stream. Magnesium atom outer concentration remains unchanged, and silicon copper atoms concentration decrease. That's the main conclusion. With the increase of strain and the micro hardness of the aluminum, magnesium, copper alloys increase and finally reach the saturation value. However, the aluminum silicon alloy so far and high stress. With the increase of strain, the grain size of aluminum, magnesium, copper alloy gradually refined, while the grain size of aluminum, silicon, copper gradually coarsened. During the HPT process, copper, magnesium, and silicon atoms show the phenomenon of segregation, partial segregation, and nano segregation and grain boundaries, respectively. During the HPT process, copper and silicon atoms continue to diffuse into the dislocations of grain boundaries, promoting the nucleation and grease of the copper precipitation phase and poor silicon particles. That's all. Thank you for your attention.
Yeah, thanks. We can have a chance to take maybe one question from the audience.
I have one question.
Yeah, please.
Hi, nice work. Thanks. So in terms of micro hardness and atom probe for aluminum copper alloy, so did you think about the nature aging effect? I mean, solute crust can form during nature aging. I mean, how you measure micro hardness? So this is right after deformation or after deformation, you leave the sample for a couple of days, because the root clusters can contribute to strength. Also, can that affect your solution element distribution? So did you think about this? Thanks.
Yeah, it's okay. I think we can communicate maybe main. If we can answer, that would be great. If
Okay,
not,
sorry.
we can chat through in the chat box, and everyone can also see that. Yeah, but it's a great question.
I just give quick questions. Because the materials decompose if there is precipitate hardening. So what we did is after the process sample, we try to keep it the low temperature before do the hardness test. So because the sample already decomposed, so the clustering effect is insignificant. So basically, it already have larger precipitates. So that is the hardness result pretty consistent. Okay.
All right. Yeah. Thanks for the comment. So next speaker will be a Shenbao Lin, also from Nanjing University of Science and Technology.
Yeah. Thanks, Chair. Can I start?
Yes, please.
Okay, thanks, Chairman. I'm Shenbao Jin. I'm from Nanjing University of Science and Technology, working with Professor Gang Sha. The talk I will give today is about the effect of atom probe analysis parameters on composition measurement of activities in 6,000 and 7,000 aluminum alloys. The material was provided by the Professor Jizi Liu in our university and Professor Yan Junli in Norwegian University of Science and Technology. The experimental work was conducted by the master students in our group, Bingnan Shi and Hao Kai-su. Very thanks to their contribution. We all know that aluminum alloys are very important structural materials and widely used in industry fields. The nanoparticulates in these aluminum alloys play a very important role in strengthening the material. But if you look at the precipitate sequence in these alloys, actually they are quite complex. The structure and the chemistry change during the evolution. The structure can be determined by the diffraction methods, but how about the chemistry? Actually, it's quite difficult to get the accurate composition of these precipitates, especially when their size in nano scale. The atom tomography is very powerful tool to solve this question. Actually, there are more than 100 papers on this issue. I mean, people using APT technique to get the composition of these precipitates in aluminum alloys. But if you look at these publications, you will find the experiments were conducted in different instruments with different running mode and different running parameters like temperature, pulse fraction, and laser energy. So there is a question whether these running meters influence composition measurement. For example, people get different maximum to silicon atomic ratio in of the precipitates in 6,000 alloys from 0.5 to 4. So we don't know this result whether influenced by the running parameters. That's the purpose of this research. Let's start from the 6,000 alloy. The material we used is the 6082 aluminum alloy with a composition like this. The material was aged at 185 degrees for 1 hour. The APT specimen was prepared by electropulsing and run in our APT instrument LEAP 4000 SI. The APT experiments were conducted on the voltage pulsing and the laser pulsing modes. We focus on two kind of parameters. The first one is base temperature. We change the base temperature from 20 Kelvin to 80 Kelvin. And also we change the laser energy from 40 PJ to 120 PJ. I have to mention that all the conditions were run on the same tape. You can see that's the atom map of this APT results. There is a pole zone, pole region with clear silicon segregation. That's because it's one tape, one grain, and one orientation. The reconstruction was calibrated by the interplanar spacing of the 1 planes. We check the background and the mass resolution. Fourthly, if we can see here under the voltage pulsing, with the increasing base temperature, the background increase. Same effect of temperature on the background can be found on the laser pulsing, the red line. The background goes up quickly after 50 Kelvin. For the resolution, we can see here on the voltage pulsing, the resolution decreased slightly with the increasing temperature, and on the laser pulsing, the resolution increased forcibly and decrease. But if we see the effect of pulse energy, we have found actually the pulse energy has little influence on the background and resolution. The background increase will influence the composition, the concentration measurement for the especially for the trace elements. For example, the copper in this alloy. Next, we check the max structure obtained at different temperatures on the voltage pulsing. You can see at 20 Kelvin, there is a large tail behind the aluminum peak here. I hope you can see the mouse. Yeah, sorry. With increasing base temperature, this tail become a narrow peak at 28 DA, which should be the silicon ions with one charge, because you can see for the mass structure of matrix, there are almost no such a peak. But for the mass structure, for the mass structure of the precipitates, the peak at the small peak here is much more significant. So I think it's silicon and with one charge. But I didn't assign any silicon peaks here. I will explain why in the next slide. That's the microstructure obtained at different conditions on the laser pulsing mode. With the increase on the laser pulsing, we can see there are several small peaks after the aluminum peaks. That should be the aluminum hydride ions. With increasing base temperature, these small peaks gradually disappear. But the background also increase, which influence the detection of copper here. The effect of laser energy has little influence on the microstructure. You can see the A, D, and E, they are almost the same. If we compare the microstructure of pure aluminum, you can see on the voltage pulsing mode, there's a very large tail behind this main peak of aluminum. And on the laser pulsing, there are several small peaks. And this tail and these small peaks are overlapping with the silicon peaks. So we don't assign any silicon peaks here and here. That's definitely cause a certain underestimation of silicon concentration in this area. Okay, that's the atomic density in the matrix and precipitates. Here, the atomic density in matrix under different conditions are quite stable. They keep in a similar level. But you can see here the atomic density in the precipitates is quite is much lower than that in the matrix. That could be caused by the local magnification effect, because in this alloy the precipitate have higher evaporation fields than the matrix. And with increasing base temperature and post energy, the atomic density in precipitates decrease quickly, which indicates the local magnification effect was enhanced at higher temperatures and higher laser energies. So, which can be seen clearly from these atom maps got from different conditions. We need to, I have to say that it's the disappearance of aluminum is much more serious than magnesium and silicon. So then we check the solute concentration in matrix and precipitates. From this figure, left figure, we can see with increasing base temperature on the voltage pulsing, the maximum concentration, silicon concentration, and the copper concentration, all of this concentration decrease, which can be on the laser pulsing, the temperature have the same effect. You quick decrease, the solute concentration quickly decrease as well. But the laser energy has little influence on the concentration. The decrease of solute concentration could be caused by multiple factors. For example, the background noise increase, which is mainly which influence the concentration detection of copper, I think. But for the maximum in matrix, the concentration is very low, so it also influenced by the background influence. background increase. And also another factor is the DC evaporation that mainly occurs for magnesium, I think, because magnesium has the lowest evaporation fields in this alloy. And also the peak overlap issue of silicon on the mass structure. And that's the right figure shows the solute concentration in precipitates. We can see actually with increasing base temperature and post energy, the solute concentration increase. That's mainly caused by the loss of aluminum atoms from the precipitates with the increasing temperature or increasing post energy. That's the next we want to calculate the maximum to silicon ratio in precipitates. But before that, we found a very interesting phenomenon. That's here is one precipitate in this outline. We can see the pure points are maximum atoms, and the blue ones are silicon atoms. Actually, this figure is from the is a parallel to the Z. Is a value. Sorry, is a view from the Z direction, and this one is perpendicular to the Z direction. And we can see the center of this maximum segregation and the center of the silicon segregation are not coincident with each other. There's a little is slight separation. And from the XY plane, and on the XY plane, you cannot see such a separation, which indicates there is which indicates that the retained field evaporation of silicon occurs. It's reasonable because the silicon has higher evaporation field than the magnesium. The separation can be seen more clearly from the right figure. We made a magnesium isosurface and the silicon isosurface. You can see these two surfaces are not coincident. If we make a persigram analysis for these two kind of isosurface, you will get different results. For example, here, this figure is made for the maximum isosurfaces. From this figure, you can see the maximum concentration is much higher than that of silicon. But for this one is made for the silicon isosurfaces. Surfaces. The maximum concentration is and the silicon concentration are almost the same. So which one is more correct, or which one is more real? Here I make a third isosurface, which is made for maximum plus silicon, and I made a persigram analysis for this isosurface. You can see the concentration is always in between the first one and the second one. So if you calculate the composition in the core region of the precipitates based on these three persigrams, you will get different results. And here the result is looking quite complicated. But actually, from this figure, you can see the effect of the running parameters and also the choice of the isosurfaces. For example, from the figure one, so figure A, with increasing base temperature, you can see the maximum to silicon ratio decrease wherever you use different whatever you use which choice of the isosurfaces. The decrease, the maximum to silicon ratio decrease with increasing base temperature. I think it mainly caused by the DC evaporation of magnesium during voltage pulsing. And on the laser pulsing with increasing temperature, actually the maximum to silicon ratio increases. I think it's caused by the which means the silicon is highly underestimated. So I think it could be caused by the overlapper issue on the microspectra. For the laser pulsing running on the laser pulsing with defined pulsing energy, you can see the composition we got is quite stable. So, but which one is more real or more correct? According to the literature, the participants formed in this line is beta double prime phase. So according to the stoichiometry in this of this phase, the maximum to silicon ratio should be 1.25 around here in this level.
So, but we're close to the end of the session. Maybe you can quickly goes to the conclusion.
Okay.
So we can still discuss.
Okay. So we see the same phenomenon. We got the same result from the 7,000 LIS. The effect of temperature and the effect of return field evaporation of zinc. So that's a conclusion. The first one is the base temperature has significant effect on the precipitation composition measurement in aluminum alloys on the both laser pulsing and voltage pulsing. My suggestion better use a lower temperature. And the second conclusion is that laser pulsing energy in the range. Anyway, laser pulsing energy can enable a stable and reliable composition measurement of the precipitates. The third one is return field evaporation of silicon and zinc is important for the composition measurement of the precipitates. That's all. Thank you.
Yep. Yeah, thanks, Bob. We're running out of time, but any question from the audience? But this is the last one. We can take some questions. Yeah, simple. Any computational tool you're using, because it's a good parametric study. Have you done any like a simulation or computational study?
No. I just do the experimental work.
Yeah, because that's it's a big parametric study.
I think yeah, I think we need some computer work to understand this result. It's very important, but I don't know how to do that.
Yeah, there's also a question from the chat. Just wondering, can you see that?
Okay, let me see. Well, no, I didn't assign any peaks, assign any aluminum hydride peaks. Okay.
Yeah. Anyway,
maybe we can discuss later.
Yeah, we have a break coming up, so that's But anyway, we thank all the speakers and Shenbao said, yeah, very nice talk. We thank all the speakers for this session. I think we can conclude this, finish this session now. I think that's, there will be a break until 1 p.m. Local time. So, Professor Gangsha, do you want to say something, or we just
no? I think that's all. And so
yeah, okay.
So we'll be back. Have a break and come back later. And then there is an announcement for the Miller Award, also the best poster. So be present, keep interesting for the rest of the conference programs. Okay.
Yep. All right. Thank you, everyone. See you maybe 1 p.m. Local time.